make sure we know how to do control around this, right? So the trajectory stabilization, the Lyapunov functions, all these things have a similar story that happens in the hybrid case. Okay, so let's think about today. Franz was nice. He sort of erased the board, but he sort of only half erased the board. Sorry. So. Okay, today, how do you stabilize first, and then even verify? Potentially hybrid, and potentially a limit cycle. Okay, and I'll do it in a few pieces. The first idea is actually pretty simple. We developed this notion of a Poincare map as, that actually analyzing the stability of a Poincare map can actually tell you something about the stability of the continuous time system. And there are ways that you can think directly on the Poincare map and design control systems and stability proofs and stuff at that level of abstraction. But there's limits to what you can do with that. Okay, and then we're going to sort of generalize this notion of Poincare map to a moving Poincare map, okay, by introducing the notion of a transverse coordinates, which is like a moving Poincare map. If you will, and then we can do transverse LQR and Lyapunov. And then it turns out once you have those tools, the hybrid versions follow naturally. Okay. And one of the key messages here, like I said, this is true of all of the sort of limit cycle lectures, is that orbital stability is a different thing to ask for versus trajectory stability. In many cases, I think orbital stability is what you want. Okay, not all cases. If you need to get to someplace at a certain time, then you definitely want trajectory stability. Okay. So we need to extend our LQR stabilization type of tools to the orbital stability case. Now I have to say, we were kind of joking in staff meeting the other day, right? That I would say you might not, this is maybe the bad way to start a lecture, but you might not use this in your life, okay? I think these days, people are more fond of stabilizing this kind of stuff with RL than they are, especially for quadrupeds, with RL rather than with the tools I'll present today. But you'll still be a better person if you understand this. And I actually want to, we haven't done RL yet, but I think the reasons that RL are working well is not because the optimization is somehow doing something different. It's just that there are robust control formulations of all of these things. And I think what we learned from RL was things like asking for a single controller to work even if the terrain is changing. That makes a big difference, okay? And you have to put all of those in to get these kind of stronger optimization results out. So I think hopefully by the end of the class, we'll sort of see how all these tools work together, okay? It's easier to do RL. This demands more understanding or whatever, but the things that are popping out of RL, I think this will help you understand what must be happening in those solutions. Okay? And I think the RL workflows will continue to evolve too. I don't think those are fully mature yet. Okay, so I talked a little bit about I talked a little bit about the slip model last time, the spring-loaded inverted pendulum. And I want to talk about that again as sort of a first way to design some of these controllers. Spring-loaded inverted pendulum. I'll use that as a working example to start. Okay, it was the one that was sort of a mass with a spring leg. Okay, we parameterize it by the leg angle, the XY position. You think of it as a point mass. It has a leg that has a length and a rest length, a spring constant. Okay, and we'll go through some of the details of that model. But let me actually just tell you where that model came from. Okay, it actually started with the story of the Leg Lab. The Leg Lab was a pretty famous lab. It started at Carnegie Mellon, it then moved to MIT. This is Mark Rabert and his students that then went on to start Boston Dynamics, right? But back in the day, they started doing hopping robots that looked a little bit like this. In fact, the slip was kind of, so Dan Kodachek and Martin Buehler and others were trying to understand why Mark Rabert's robots worked so well and distill it down to their essentials, and they built the simpler models like Slip. Okay? And then we built our rigorous understanding back up from those. But it started with these hopping robots, these pogo stick robots, right? And this is before passive dynamic walkers. This was the time where most walking robot research was actually quasi-static. We'll talk more about the definitions of stability for humanoids and the like, but they were moving incredibly slowly, these lumbering, complicated bipeds. And this is in the early 80s. Mark started building these robots that just, and in fact, some of you probably heard him. He was on the Lex Friedman podcast just recently, and he was talking about back in the 80s, he saw these robots walking around. He's like, well, that's just wrong. That's like not how biology does it. And he started thinking about how to build a simple thing that would just throw itself through the air and be much more dynamic than it was before. And the first version was a single leg. It's actually a very clever design. There's a boom here. I actually have the boom from the Leg Lab in our lab. I kind of grabbed it before it got thrown away. But there's a planarizer, if you will, that so there's a pole that goes directly back into that image, into a point, and it hops around on a big circle. So it doesn't have to worry about falling over sideways, okay? And if the circle is big enough, then it's mostly okay. But you'll notice that there's like a long body with weights on the end. That's to give the body relatively a lot of inertia relative to the leg, okay? And and there's a hydraulic control system that's actuating the hip, but a pneumatic one in the leg, because you wanted an air spring in the leg, okay? And it was just a beautiful, simple design. And they built a series of robots. I actually don't have a video of this, of the monopod, the planar one-leg hopper here. But they built a series of this. They added a second leg, looked like this. They started having this hop around the planarizer, and they put obstacles in, did all kinds of things. They built a quadruped. This is actually like shockingly good. This is 86 or something like this, 1986. Before Big Dog or anything, but they kind of just, did it again with Big Dog and did it incredibly well. What's interesting, if you look through the whole story, the way they control the quadruped is basically, it's a beautiful paper. It says running on 4 legs as though they were one. So they actually take the control system that worked for one leg and just kind of run it 4 times during the gait. Okay, just absolutely beautiful. This is in the basement of what used to be NE43. That's where I started. I came to MIT in 2000, I guess, and I went down to the basement and looked at all these robots when I started. And there was a 3D. This is just outside there. It's not an Akamai building, but it's just across there. Okay, had a 3D biped that was running around. Okay, and that robot was actually the first that I remember that actually did 3D unassisted flip, right? Now that's all the cool robots do that. Okay, this is the best one. So you can find, I showed this one because you can find this if you dig enough on the website. There's no like public link, but if you like go through you can find this on the website. I actually found the VHS tape that was on the shelf, and you can hear like the terror in their voice, like the before and after, you know, and then right after they do the put it out. You see like all these really famous roboticists like running in, trying to extinguish the flames very quickly. But that was great. This is, I guess, when you have a boom, you have to make almost a ring of fire. Okay, so let's just take that as a motivation to think about the simplest version of this again. So, yeah, you can ask. Come on, we're fun now, right? Yeah. I mean, if you take 20 years of footage and you take the best one, then that's like make you look pretty good. Okay, so yeah, quite mass at the hip, massless leg. Let me write down the assumptions carefully here. Massless leg and toe. That has a lot of implications. Okay, so if you have no mass at your toe and you have a perfect spring in here, then that implies that you basically don't have an impact. When your foot comes into contact with the ground, the reason you would lose energy is that you were somehow dissipating energy into the ground. But you have a perfectly elastic collision. You can ignore energy losses. No impact. Okay. Also, if you have a massless leg, then basically you can reorient your leg angle instantaneously, which is of course nonsense, but that's just that's the abstraction here. The limit of the mass going to zero, basically we can change, instead of thinking about torque control for the hip, we can just think about commanding the angle of the leg. At least when you're in the air. And I guess if you have perfect elastic collision, then the other thing that happens is energy is always conserved in this system, actually. Your actuator, in some sense, is doing no work since it's moving a massless thing around. You're losing no energy at the collision, so you actually have a energy conservation in the total system. Which is a weird thing, because actually the stability from the rimless wheel came from losing energy. Okay, so this thing turns out has these stable limit cycles, almost. It's only stable up to an energy. If you were to go in and push it in a direction that added or removed energy, then it will never dissipate that energy to return. So it's only stable up to the manifold of constant energy. Okay. Now the dynamics of this, which underlie the dynamics of the Rayburn style controllers, are a few things. There's a hopping height controller, which you'll actually study on your problem set. But the one that I want to think about here is actually the foot placement controller. Okay, so what Mark observed and what happens in these slip models is that, I should say Mark and his students observed, right? So if you come down at a certain angle, there is some important angle of touchdown where you have sort of a perfect symmetry. And as your spring compresses and then uncompresses, you'll leave basically at the opposite angle that you came in at. And you'd expect maybe at steady state that you're in that symmetry, and you're keeping sort of a steady state hop. You can still take off, be in the air again, but the angle you want to come down at gives you the symmetry and a periodic solution. What's interesting is if you were to then think about what control looks like for this system, if you were to, while you're in the air, choose a slightly different angle relative to that symmetric gate. If I would put my foot out a little farther to the front, okay, maybe a little bit farther to the front, then I can actually, my trajectory that you would have gone like this now goes in and actually comes up at a higher angle, because I've put more energy into my horizontal and I kind of don't turn over as much, and I end up leaving it a more horizontal direction. If I come in shallow, like this, then I'll actually leave more horizontal. Since energy is conserved, when I make this choice of putting my foot out in front, I'm trading horizontal kinetic energy for vertical potential energy. Okay, I'll hop higher on the next thing, but I'll move less. I'll move at a lower speed going forward. And this one allows me to do the opposite. Okay? I'll hop lower, but move forward faster. Okay? The physics of it is not essential, but it's sort of cute and nice. Okay? And there's a notion here of the way we're going to do control is to think about foot placement as a control strategy, and a decision that is effectively made once per hop. Okay? When I'm in the air, I think about where I am currently compared to my desired hopping height, desired hopping speed, and I make a discrete choice. What is my touchdown angle of my leg? Okay, and then I go through this motion, and I'll find myself at a new hopping height, a new hopping speed, and then I'll once again make a discrete choice. Kind of like once per period, I get to make a control decision. Okay? So let's think about how that plays out with our basic toolkit. The slip. Yeah, please.
Discrete choice, continuous option.
That's true. Yes, that's right. It's a once per step, continuous decision.
Are we also, so like I don't understand why the mass and the software moves for like it's carrying the velocity while are we like sort of assuming infinite friction at the point of contact?
Yes. So once you're in contact, you have infinite friction with the ground. That's true. I could list that as an assumption. Yeah. So when you're in contact with the ground, you just go through the passive motion. Suddenly you went from a massless leg to like you have the mass of the earth. And so you have no control authority. Good. Okay, so a standard analysis of the slip would be to look at the slip apex to apex Poincare map. Okay. It turns out, if you're clever and you make a few assumptions, then it's actually, you can write the Poincare map in one variable and analyze it a lot like what we did for the Rimbus wheel. But and those details are in the notes. But I think for the purposes of control, what's important to think about is that I'm going to think about the apex to apex, apex meaning the highest point that the hopper reaches in each cycle. Okay. Which was defined by the vertical velocity reaching 0 before it turns back down. Okay? I can use that as my surface of section for the Poincare map and define a Poincare map that goes okay, so this is the the state on the Poincare map at the nth crossing. Right? And then this U in this system is the once per step. It's the action taken on the nth hop. And given a choice at the touchdown angle in my current state on the map, I can run my simulation dynamics forward and figure out what my next apex is. Right? That map is fairly complicated. I don't have a closed form solution for P. It requires solving a differential equation, which I can't solve, so I numerically approximate it. Okay? But that map exists, right? There is some function P that maps that. It's actually pretty well behaved. Until you get to crazy things like you put your leg horizontal and or you don't have enough energy to actually go. If you put it at too much of an angle, you won't have enough energy to even get to vertical, and you just fall back the direction you came. But in the sort of normal regime, it's a well-behaved, nice, smooth function P. If I change my hopping speed or hopping height a little bit, I get a smooth change in the next one. Okay. So I gave kind of a physical interpretation of how I might be able to write a simple controller. But once we think about it as a smooth, nonlinear map, there's a bunch of different things we could potentially do to stabilize that. Okay. If our goal is to write a controller that is, U of n is some pi of xp of n, then the first thing we would do, since you've been hearing LQR all semester, right, would probably be to linearize the Poincare map and just do LQR. And that works. Right, so I can approximate P of x u as approximately P of x naught u naught plus partial P partial x, evaluated at x naught, u naught. All the same things we did before, right? Get myself a linear system in the time varying, in the error coordinates. Let me make discreteness super clear. And I can just write an LQR, a quadratic regulator objective. And this will, if I've computed P properly, right, this will actually figure out that physical intuition I just told you, right? It'll tell me how an incremental change in my touchdown angle will affect XP at the next step. And solving for the LQR, this is a discrete LQR. And it's funny because I would normally say discrete time LQR. That is how we're mapping it. But in some sense, time has been removed, right? The notion of the actual clock time that's taken between the apex at n and the apex at n+1 it could be different depending on the path it takes. Right? But we still we use the tools of discrete time systems to find that controller, and it will tell me if I'm a little bit too, it'll figure out exactly that sort of logic. Yes? let's say that if our control objective is specified as stabilizing a stabilizable fixed point. Okay. Same thing we did for the other LQR. You want to find some nominal XU pair that would be a fixed point of the P. Right? And then you can stabilize that point. Good question. Thank you for asking that. So you do, if you don't stabilize a stabilizable point, then we would have to do some of the more, stabilizing trajectories. You could do something like that. But for LQR time invariant sort of stabilization, you want to be stabilizing a fixed point. Yeah. So your first step would be to find a fixed point, let's say, of P. That's true. Good. Now, what you said was almost exactly right. The state of the system would be x, y, x dot, y dot. The theta is just a little weird because we assume that the actuator is theta. So U is kind of theta in this particular case, but otherwise everything you said was exactly right. Okay, so the algebra is just what you'd expect, but what I want is for you to grok what happens, like why does LQR, discrete time LQR, allow you to stabilize a limit cycle? The Poincare map abstracted away the details. And the strong things about these Poincare theorems is that if the map is stable, then the vector field must also be stable. Right? For me to return to the map and have a local convergence in this, you can't do different things when you are going around the circle. You must have done something that gave you orbital stability on the limit cycle in order to have achieved stability on the Poincare map. Similarly, in the case where you have actions abstracted to once per cycle, you can just do the discrete time stabilization on this Poincare map, and if you stabilize the Poincare map, you stabilize the cycle. Okay. It's super clean, super good, I think. It's limited in the sense that you have to, at the moment of being at the apex, you have to decide basically everything you're going to do over the cycle. Your feedback, your decisions are made only based on the state at the top. If something happened to you in the middle of your hop, you're not going to respond to it until you got to the next thing. You've only made one control decision per hop. But in that case, the Poincare map tells you everything you need. Okay. Questions about that? Yes, that's just it. I mean, you could pick a different, surface of section for this system. It happens that the apex is the one where it really reduces to a one-dimensional map. Because if you know that energy is conserved, you know your velocity is exactly zero at that point, then you can basically just use the height as the only variable you need to know, and it'll tell you everything else about what your state must be doing.
In principle, I guess you could have multiple maps along the way, and then you can get more perspective.
Beautiful. Okay, so what if we were to, like I said, if the limitation was you're making one decision, what if we were to place sort of a few different surfaces along the way? Right? There's even a more beautiful version of that, which is we're just going to drag our Poincare map all the way around the cycle with us. Okay, so that's the limiting case of your idea. Perfect. Yeah. There's a version where you can sort of drag it along. Cool. It turns out actually for SLIP, I would say this is a little bit of a specialized solution, but it's so elegant, and there is a general principle in it. Okay. Turns out that for SLIP you can do better than not better than LQR. LQR is optimal for the quadratic regulator objective, but there's another natural objective for the SLIP, which is the deadbeat controller. So the LQR says, I would like to penalize over multiple steps the quadratic error distance from my desired fixed point and the quadratic effort I put in, right? You can choose a different cost function. The deadbeat control is an extreme where it says after exactly one hop, I want to be exactly at my fixed point, no matter what action cost is necessary. Okay. The deadbeat controller is kind of find me the u such that p of xp, even just like this, my current xpu equals my desired xp. You can't do that with continuous time systems. You can't say, like, in 0 time, I'm going to achieve my goal. But with discrete time systems, it is possible that with finite action, over that entire hop, you could be exactly at your goal point in a single step. That's called the deadbeat controller. Okay. So, in this, cartoon picture, if there's a certain height I want, I could just basically simulate many different touchdown angles and find the one that gets me in a single hop exactly to the desired fixed point. That map turns out to exist and is sort of well behaved for a large range of these parameters. It's got a nice solution. So the deadbeat controller is another option. Now, it turns out the reason that the deadbeat controller is so awesome for the slip, okay, so in both of those cases, in order to evaluate P, whether it's for LQR linearization or for the deadbeat controller, it means you have to know sort of X, and I used Z here, I'm sorry, I used Z here and Y on the board. You need to know your height of your object and maybe its velocity, for instance, at the apex. Implicitly, what that means is you have to know where the ground is, because I'm defining Z as the distance to the ground. Okay, here's a really cool trick. It turns out, if you were to take Z, okay, and start moving the robot up and down, okay, and looking at the solution to the deadbeat controller for a particular hopping point, it turns out that as you move down, the leg sweeps through an arc smoothly. This is a little bit of a convoluted argument, but I hope you stick with it, okay? If I were to just look at from different Z's, what the optimal going to some particular nominal hopping height would do, it's going to change my leg angle smoothly. So Hartmut Geyer made this awesome observation. That means you don't have to know where the terrain is. It turns out, if you're just hopping along, and you just pretend that I'm going to hit the terrain, at a certain time all the time, and you just close your eyes and sweep your leg through this schedule, then whenever you happen to hit the ground, you're going to be in the right place. Okay? So there's a blind, open loop, deadbeat controller for the slip model that doesn't have to know anything about the terrain. Right? Yes?
Does the terrain also have to be flat?
You come at a point, so it doesn't really matter. Basically, wherever your leg enters. I mean, maybe you want to ignore the collisions between your leg, but if I drew a mountainous terrain that happened to go like this, then the dynamics are the same. Right? And I probably should do that to make my videos look more impressive, but I don't. Never learned that lesson properly. Right? So here's Hartmut's observation that he can stabilize blind open loop hopping where the terrain. He also didn't learn the lesson. He did piecewise smooth. Maybe it's more pedagogically clear like this, but this hopper doesn't need to know the touchdown angle. Oh, I should have included it. There's actually there's great work. There's a great video of like a guinea fowl running on a over this sort of terrain, and the experimenters kind of a little bit mean, but they put this on the track where the guinea fowl is running. They put this paper, like breakaway paper. I don't know. It's really soft, like tissue paper or something. And there's kind of a gap in between it. But visually, the guinea fowl doesn't realize it's about to go over a cliff, okay? And this guinea fowl runs along at high speed, and its foot goes down, and it basically just doesn't even notice. So like it just keeps going, you know, horizontal. You've seen it? Yeah, yeah, right? And it just takes it in stride and keeps going. Right? That's by Monica Daly. So there's something like this maybe that's kind of right about what biology is doing. Yeah?
I think it's a bit different, but the cockroach is something else.
I've got the cockroach coming. Yeah, don't take my punchline, man. Yeah.
So it seems like most of the complexity here is in writing down how like keywords evolve.
Yeah. You don't typically have the ability to solve for P analytically. You tend to do it by simulating forward. Yeah, that's right. You only have a numerical evaluation of P. But if you can, in the slip case, you can sort of just solve it once and learn this curve. But in an online case, you might be taking gradients by simulating forward and doing basically a trajectory optimization kind of gradient to get the gradients of that map. Yeah? Cool. Yeah, of course. Yeah. So, I mean, it's a funny thing. Okay, so it seems like you need some like world reference at some point just to like position yourself. But if you're, let me think how it goes. All of the things are combined. So if you don't want to think about it in terms of apex height, you can think about it as horizontal velocity in the part where the apex is 0. There's a kind of like variables change, but I think effectively, let me say it a different way. Forget about the world frame. If I sweep in an open loop schedule, then I will come to rest at some hopping height that is relative to the world y. Okay, and there is a little bit of a game, I guess, to find what's the energy that sort of achieves that, but because it's also constrained by your total initial energy of what you can possibly obtain. But I do think it all kind of works out. I think you can put yourself in a coordinate system. If you know the total energy, then you'll know what height is possible, and the terrain can move up and down relative to that, and it all works out. Okay, so there was 2 points to this. One was just a little foray into some running robot stuff, but also there's kind of this idea that we're doing control directly on the map. One last thing I'll say about the slip model, right? So, and it goes towards cockroaches here, but you might think that this is just way simple, right? And like massless leg, like that's obviously fake, right? It turns out it's been incredibly useful as a model, as a simplified model of how animals run, right? So the history was that Raybert built his hopping robots, but then Kodachek and Buehler and others started making these simplified models. And then Kodachek and others started to collaborate with Bob Full, biologist, okay? And they started looking at the gaits of animals, okay? And they started analyzing them through the lens of slip, okay? So in particular, they looked at the trajectory of the center of mass relative to a canonical frame. If you have multiple legs, you could still think about at any instantaneous point in time, your center of pressure as kind of being the single foot, okay? And you look at your dynamics of your center of mass, and it seemed to take this sort of spring-like center of mass trajectory through stance, and then it naturally takes the gravity center of mass trajectory in flight. Okay, so that was sort of an interesting observation. And then they're like, well, what's the spring constant? Like, is that a reasonable spring constant for the slip? And it turns out that you have to make a dimensionless spring constant if you wanted to compare cockroaches with horses and stuff like this, okay? But there's like a huge range of different animals. And they all seem to put themselves in the same sort of dimensionless spring constant of this kind of canonical slip model. And that's like a cockroach, which runs very differently than a horse, than a human, than a kangaroo. You know, some of them have 2 legs, some of them have 4 legs, some of them have 6. I don't see any 8, but you know, like like the crab is running sideways, right? But its center of mass is kind of doing that sort of same thing. So, I mean, everybody thinks it's still simple, but Like to first order, it was surprisingly descriptive of what the center of mass trajectory of these robots look like, and their ground reaction forces. So if you look at a treadmill when they're running, okay? And then the best cockroach one, okay, so it turns out that they're like, okay, well, it works for the vertical direction. Does it work for the horizontal direction? So they started understanding how different animals would respond to horizontal lateral perturbations, okay? And it turns out that the cockroach has kind of a spring-like response to horizontal perturbations, okay? But when I say that, what you should ask yourself is, how do you perturb a cockroach horizontally, right? Okay, it's awesome, okay? This is how you perturb a cockroach horizontally. You bolt a cannon to its back, because they're fast, right? Okay, you bolt a cannon to its back, you explode something like this. That one actually had an impact, so there's two, whatever, okay? But Devin Gindrich made these experiments, and I just thought it was the funniest thing I've ever seen, right? And but the amazing thing was that well, there's a couple amazing things about that. First of all, they have a spring-like behavior. Second of all, they're super robust. You know, you could not only can you bolt a cannon to its back, and it's like, that's my exoskeleton, I don't care, you know, and then, but it not only, you can see how quickly the orientation recovers, but what's amazing is in all the data, the horizontal, like the total velocity vector, actually recovers within a step. So one of the key findings of this was that which is consistent with this lateral leg spring idea, is that there's not actually enough time for the neural signals to travel from the legs to the spinal, it's not a spinal cord, what is it, whatever the neural network of the cockroach, you know, back. The time it takes for those synapses to fire is too great to describe the mechanical response of the cockroach to the perturbation. They think it's actually the mechanical stiffness of the leg that does the first response, right? So it's not just that we're choosing with our brain to act like springs, it's that we are actually springy, and that's essential to our stability. Okay? There's like so many good experiments from these guys. He had an experiment for measuring ground reaction forces of cockroaches, right? Which was just so good. Like he made Jell-O, okay, and he put like diffraction, basically shined a light through, and when the cockroach stepped on the Jell-O, it would bend the light and allow force visualization to come through. So clever, these guys. The hilarious thing is Devin, at one point when I was talking to him on the side, he said something like, it's surprising how little gunpowder is required. And I'm just thinking to myself, what were the first 5 experiments? You know, like he never said anything like that, but it just got me, got me thinking. Right? Okay, so that's animals. Maybe you don't care about animals, right? I mean, you should care about animals, but if you look, when people ask like, why do quadrupeds work so well lately? I think there's a couple stories. I do think control has gotten better. That's true. But I actually think one of the things that has happened that people underestimate is that the mechanical design of our quadrupeds changed dramatically. Spot was one of the first, but if you look at all of them nowadays, everybody figured out you want a relatively massive torso with some inertia, and you want super light legs, right? Mass approaching 0. Limit as mass approaches 0. Why? Because if you can move your legs super fast, then it's pretty hard to fall down. Right? So actually, a lot of the revolutions, I would say, in quadrupeds is when we started building these, actuators up in the body, mostly up in the body, super light distal, legs.
Do they pad the body with extra mass?
The Raybert hoppers very explicitly did, right? I think a quadruped doesn't, already has an elongated torso. What matters is your inertia relative to, so basically, you want the assumption that when you move your leg, your body doesn't move much. So you want the inertia around, let's say, the y-axis. If your hip is, your pin joint's in the y-axis, you want that inertia to be big. And quadrupeds are sort of naturally have that. The Raybert hopper, that's why it had a boom, and with the weights off to the side to make that assumption good. Okay, let's get to moving Poincare sections. Yeah, sure.
Our feet and stuff are not so super restless. So is that some trade-off in stability for certain walking speed?
Yeah, I mean, humans are kind of, not great, right? As locomotors, I think, right? I think we probably gave something up to be standing more often than we're running. Right? I think most animals do have pretty lighter. I mean, you can go up and down the animal kingdom and decide, but I think, for instance, we said before, but the birds, you think about birds having backwards knees, or even dogs having backwards knees, but it's actually not that. It's actually that most of the dogs' lower leg, it's actually their heel is up where you think is their knee, and all they have down there is like their toes. Right? Okay, and then their hip is actually tucked up in the, their knee is kind of up by their hip, kinematically very close. And I think there's a lot of stories about how you keep the legs really light. I remember, you guys, sorry. I remember when I was in the leg lab hanging out, and we had a talk by someone who studied horses. Like, he was a vet, and he studied horses, and he talked about the way people say that the forward speed of locomotion is dominated by your ability to swing, how fast you can move your leg forward. And the reason a horse is fast is they have super light legs, but they also have these big tendons that wrap around the hip. Okay, when you're in stance, it's actually like loading up a big catapult. And then when you lift it up, you're shooting your leg off forward. And that's what allows them to run. They move their leg forward faster than their muscles are capable of producing those kind of power curves. Right? So it's all about keeping your leg, and you think the horse's leg is super light down there. All right, math. Let's think about moving Poincare sections. Exactly motivated by Adam's question, like if I'm limited so far by making a decision once per step, why not put a few surfaces of section around there? And more generally, we want to think about just a continuous Poincare map moving all the way around the cycle. So here's a simple example would be a ring oscillator. Okay, so imagine like the simplest oscillator, which is just like written in polar coordinates. That is not as round as I was hoping. Q dot, then that's round. Okay, get another color. You can write a dynamics simply enough that basically the radius has a dynamics which just converges linearly, and the phase sort of variable, the angle, just goes around with speed 1, and that gives you a nice stable limit cycle that looks like this, sort of simplest ring oscillator. Okay, and so you could definitely do the standard Poincare analysis on this. Right? I could pick a surface of section like this, and I can analyze by integrating the dynamics over a cycle and coming back and doing all my Poincare analysis. But in addition, so in the control sense, this is limiting because it will only make control once per. Even in the analysis sense, it's limiting because I have to integrate across to get P. What I'm going to do instead is try to make a same side of kind of Poincare argument, but I'm going to define this as just a moving Poincare section that moves all the way along the orbit, okay, and see if I can use the same kind of some of the same Poincare specialness to get the orbital stability instead of trajectory stability. That's key, right? But without having to do the sort of the integral. All right, so let me just make sure that that point lands. Okay, so if I were to look at the dynamics on a moving section, okay, but this section is not, let's see, trajectories on this section might be moving at different speeds. I'm setting up a new clock, okay? And the trajectories along this, this moving section, time is being abstracted away, right? Trajectories out here might take a long time to follow the same moving section compared to a trajectory that's in here, right? So I'm abstracting time away, and I'm again defining the state as being only examining the states on this and examining how it moves relative to the section and abstracting away how the section moves. Okay? So let me show you the mechanics of that. Here's sort of the math of that simple ring oscillator. Okay, and the picture I want you to have is, again, this is my bad board work, but I want you to have this sort of picture of, for any limit cycle, even in high dimensions, we're going to pick some surface of section and we're going to move it along the cycle, and we're going to look at the dynamics on that cycle. Okay. So what we'll do is we'll define on this cycle two things. Basically, we'll define this coordinate as x perpendicular. Okay. The map we'll define as a function of tau. So tau is going to be kind of our phase variable here. And then I want to write the dynamics of tau. Okay. If I'm in, I mean, okay, this is a funny, I said it in a slightly funny way, but really I've just written the system in polar coordinates, if you will, almost, okay? So I can write the dynamics in polar coordinates. That doesn't sound funny at all. But if I think about this as surface of sections, then let me write it this way, okay? I can tell you how time is evolving if I'm in any current, sorry, this is going to be tau here. I can completely tell you what state I'm in by just knowing which section I'm in, which tau I'm in, and what my coordinate is in that tau. Okay? And as a function of x of those things, that complete representation of the state, I can tell you how time is evolving, and I can tell you how x perpendicular is evolving. It's just a different coordinate system to write my dynamics in. And again, for the simple ring oscillator, it's just like polar coordinates. But something cool happens here, okay? I can combine sort of the ideas of time-varying Lyapunov functions with this sort of transversal coordinate system to talk about orbital stability. Okay? So the picture I want you to have in your head is I'm going to just define a Lyapunov function that looks like this, which is defined on the transverse coordinates for every tau. Okay. And what I want to say is that basically I move down in a Lyapunov function, and that will tell me that I'm going to converge to the cycle without telling me the dynamics at which I'm moving around the cycle. It tells me orbital stability instead of trajectory stability. Right? The picture for the Lyapunov stability along a trajectory was I've got a quadratic bowl and it's moving forward along the trajectory at the clock rate of my nominal trajectory. This is a different object. I'm going to define it like this, and it's only going to tell me that I'm converging to the trajectory. And maybe I need something else just to say that tau dot is at least greater than 0 on the trajectory, just to make sure I go around and don't just get stopped at a fixed point. Okay? But we want to think about an object that looks more like this, convergence to the trajectory in orbital stability. And it turns out that the Lyapunov conditions are almost exactly, they're just a small variation on what we've seen before. Okay? If you can find me a a Lyapunov function like this, right? Smooth and all the things, such that for all tau, v of x tau is greater than 0, except for v0 tau equals 0, right? Same sort of thing. And for all tau, v dot x per tau less than 0, except for v 0 tau equals 0. Then I can talk about convergence to x perp is going to converge to 0, which is like that picture. Yes?
What is derivative?
Yep. It's with respect to both variables, but you'd like to say that it's kind of like the total derivative here. You can write it, if you use these coordinates, then you have to write both components of it. Still looks like that. It's the total derivative in time. You want to just think of an energy function that's going, as trajectories evolve. Right? This term here, you might think isn't doing anything when you're at the origin, but it allows you to just it allows you to make the statements that you could imagine things that allow you that go uphill a little bit, but downhill again, that wouldn't work without that term. Yes.
Is it typical to have the same Lyapunov function?
Not needed. Right? You could have any positive definite function. It could stretch and shrink, whatever. What you'd like is that it converges to 0 on the orbit. Okay. But by virtue of abstracting time away, right, by saying, this is holding for all tau, we're getting a different type of stability. We're getting orbital stability instead of trajectory stability. As opposed to a quadratic function that's moving on a clock, we're just saying we converge to the trajectory. You might ask, how do you get such, how do you find a Lyapunov function like that? How did we find Lyapunov functions in the fixed point case? We did sums of squares ultimately, but how do we get an initial guess for sums of squares?
Take the Lyapunov candidate as linear.
Exactly. You can take the linearization around a fixed point, compute the Lyapunov candidate, right? In the trajectory sense, we did that again. We said you could take a time-varying linearization, and you could get a time-varying Lyapunov candidate by solving the time-varying Lyapunov equation. Guess what? You can do the time-varying version of this, the time-varying linearization of this, but now it's not explicitly varying on time. It's a function of tau. Okay. So we're going to call this the transverse linearization. I'll start here. Okay. I didn't say the word transverse before, right? So to make the conditions on the phase portrait on the surface of section is that this x perp coordinate has to be transverse to the orbit. It just means that the trajectory you're trying to, or the orbit you're trying to stabilize, it can't move along x perp. Otherwise, you wouldn't be a complete state representation, right? It would lose rank or something like this, right? You want the condition that the flows go through the surface of section, even the moving surface of section. That's why it's called transverse. This x perp coordinate is one dimension less than the original state coordinates, and you just want to make sure that your flows move sort of through that if you were to fix tau. So we call this transverse coordinates and transverse linearization. can get, by linearizing this, right, you can get x perp dot is approximately equal to a x perp plus b u, okay? But these will be in general functions of tau. Maybe they're going to be a bar error coordinates here. Make it a little bigger, a little neater here. X perp bar dot is approximately equal to a, the function of tau now instead of time, x perp bar, okay, plus b, still a function of tau potentially, u bar. That would be the natural linearization along this arc.
So, as mentioned last time, we learned the Poincare map, but now this state along the Poincare map is one-dimensional less.
Yes.
And yeah, I guess I just set it up where you're showing two dimensions because you have the one variable you're interested in and you have its time derivative. But does it really make sense for more than two dimensions? Then, like, what are you?
I'm not able to draw well in this, but this is trying to lift that up into at least not, explicitly stuck on two dimensions. But you really, I mean, to write your state in a new coordinate system, you need a total of n numbers in general, right? Unless you know something else about equalities. One of them you're choosing to be tau. So that parameterizes one value, and then the other n minus one is this parameterization of the subspace that is transverse.
Here you're now oscillating between Q and Q dot. In more dimensions, you would be oscillating between a lot of different stuff, and specifically Q dot.
Yep.
What makes Q
Sorry.
special?
Well, it's tau. So even tau is changing its sign as it moves around. It's not only Q dot, right?
Right. So all of the different Qs, as you increase your dimension size beyond one Q, all of these Qs they still have a unique relationship specifically to Q dot instead of Q2 dot or Q3 dot or Q5.
Sometimes you can easily relate your coordinates to a single variable. Like actually, for a lot of the walking robots, it turns out that if you just think about like the angle of your lowest leg or something like this, there's kind of a total body angle, then you can write your whole cycle just as, you can kind of choose that as your tau variable, and that works. But in general, it need not line up with one of your variables, right? This orbit need not line up with so neatly with one of your variables. Let me give you a recipe for finding coordinates, okay? So if you just take along your trajectory, you take the derivatives along the trajectory, so anywhere you can find the vector at that point. That's one vector in an n-dimensional space. You just need to parameterize the null space, the perpendicular space of that vector. Right, so instantaneously you can find any coordinate system that lives in the n-1 that is orthogonal to this. Right? That is a recipe. There's some tricks to try to make sure that that mapping as you move the trajectory is smooth so that vectors aren't jumping around. You don't want to just like call your null space kernel in your linear algebra package independently on every time step. You want to have a smooth mapping, but it's really just looking at the kernel of that sort of projection. So what matters is that it's orthogonal to the instantaneous vector and a complete parameterization of the space. Sometimes it lines up, sometimes it doesn't. And the reason that matters, again, is because we want this picture, right? We want to separately handle stability off the trajectory from stability on the trajectory. That's the key idea. We want to just talk about the dynamics of the transverse coordinates. Yeah. Yep. So it's typically your nonlinear dynamics. put through that projection, that change of coordinates. Yep. So it's kind of algorithmically, you can find it in 2 steps. You evaluate your multi-body equations or whatever, and then you change it into those coordinates. Cool. So if you have a passive or a closed loop system, then you can get a transverse linearization that just looks like this. You can call your Lyapunov equation. You get a quadratic as a function of tau Lyapunov candidate, and it really does look like that. Although it could stretch and shrink as it moved along. It doesn't have to be the same quadratic form all the way around because it's a function of tau, right? But really, it's the same tools we've already invented. But this time, it's doing orbital stability instead of trajectory stability. Remember back when I said, it's tempting in LQR to just say, let's look along the trajectory at the closest point and just project and use that K. You can't do that for LQR, time-varying LQR. You can find situations where that would blow up on you. But if you do a controller, if you do the LQR in the transverse coordinates, then it is exactly doing that. The way you would, so if you wanted to do transverse LQR now, this gives you U bar is some K as a function of tau, X perp, okay? And the way you actually implement this is you actually say, you find tau is defined as the argmin over tau of x minus x of tau, exactly the orbital stability definition. So you find, you got your point here, rather than finding the schedule, you actually find the closest point on your trajectory, and you basically project onto that and use that transverse coordinate. I said that badly, but the transverse LQR is exactly the one that does sort of this magical, don't have to get stuck in time. It doesn't solve every problem. If you want to swing up a pendulum, okay, you don't actually want transverse LQR because you'll never get to, won't guarantee you'll get to the top, right? You'll stabilize something, but it doesn't actually guarantee that you've gotten to the end. Right? But for limit cycles, where you know you're going to be going around in a circle, this is exactly what you want. You can write sums of squares on this. Let me jump ahead a little bit. This is like using transverse LQR to look at the region of attraction of the rimless wheel. Okay, this is the eyeball, the pendulum eyeball. This is the upright fixed point. The limit cycle goes like this, right? This is something you've seen before. We actually know that the real region of attraction of that fixed point is very big. It's this light pink thing. Okay, there's lots of initial conditions that get me back to that limit cycle. But if you search for only tau varying quadratic Lyapunov functions, and you use sums of squares to do it, then you can find that as a certified region of attraction. Always the inner approximation of the region of attraction. Okay. If you think about the compass gate, it has a smaller region of attraction, but you can do the same kind of thing here, okay, which is you can find quadratic Lyapunov candidates that move along the cycle. You can verify the Lyapunov conditions with sums of squares, and you can certify the region of attraction of the passive compass gate. And you can also do, I think I have an old embarrassing video of us playing with time-varying LQR on a compass gate, okay? This is before the toe actuators working, so we put blocks down so we didn't scuff our toes, okay? We used to play with this a bunch. That's because the wire ran out. That wasn't like that control. That was the wire. Interestingly, for the compass gate, if you try to stabilize it in time, okay, LQR works very badly. The K matrices the S matrices you get will say that you have very high cost, and the K matrices you will get become very high. Because the compass gate does not have enough authority, really, to catch itself up in time. It takes so. If you solve the transverse LQR, you get beautiful small gain matrices, okay, and controller that runs until your wire runs out. Okay, there's one more idea that I'm kind of like trying to land the key ideas here. There's one super important idea. I kind of snuck in there the notion that I went from a limit cycle with no impacts to a limit cycle with impacts. And I didn't tell you how I did that. Okay. And it goes back to this picture like this. It doesn't actually have to be a limit cycle. How do I want to stabilize this kind of picture? Well, if you do the transverse coordinates, okay, then there's a freedom there's an algorithm, let's say, for picking your transverse coordinates. But one of the things that you want to do is you want to line up your surface of section with the linearization of your guard. Okay. That it's not strictly necessary. You can accommodate all these other things, but it makes everything much easier to analyze. Okay, so that at least locally, okay, transitions from this surface of section move to this surface of section, and you can analyze the dynamics in pieces. You can look at V dot being less than 0 along here, and delta V over the impact being less than 0 in order to sort of converge, okay? Similarly with LQR, we can do the transverse LQR, and you take linearizations that try to line up with the surface of section so that the time-varying dynamics can be evaluated with a smooth, continuous time Riccati equation, a jump, the one step of the discrete Riccati difference equation, and then the continuous Riccati equation backwards in time. So I kind of, I've been doing a dance between limit cycles and hybrid. They happen to play together algorithmically for two reasons. One is that walking robots are hybrid, so you kind of have to do both. But this is actually the subtle other reason, is that some of the computational things that we do for limit cycles and this orbital stability happen to also be very natural for dealing with impacts, because you can restrict your attention orthogonal to the collision events. Okay, so when you do RL, okay, for instance, I think certainly if you wanted to analyze the performance of an RL and sort of come up with a rigorous certificate or something like this, I think the underlying dynamics are doing something very much like this. I think this picture, even if you don't in practice end up designing surfaces of section and doing the analysis in this coordinate system, I think this natural picture of flows and that convergence to the nominal limit cycles being separate from the convergence along. I think these are fundamental pictures about the fundamental statements about hybrid limit cycles that must exist. Okay, let me just end with one last point about this. There's one thing I hate about this picture, this general picture. This has been very clean for control design analysis. It gives a very clean picture. Modes, guards, discrete impacts, extremely good for a lot of things. But there's one thing that's just wrong about it, which is that it treats collision events like a wormhole, okay? Where the state in this mode, in this framework, the state of this mode, it doesn't even have to have the same dimension. It could be that you've just gone to a completely different dimension, in the multiverse, over here, right? There's no relation between those. The only relation is that you've defined in a reset map that jumps into this new world. Okay, and that's not how contact actually is, right? So in practice, it becomes more difficult and fragile to have stability that, for instance, takes a different mode sequence. Like if you had a nominal trajectory and you got bumped, and you really should take a different sequence to get back. It's hard to get that out of sort of these kind of control ideas because it just it makes the impact event look too severe. So a lot of work that we've done as a field since then is kind of softening this picture, understanding the relationships across these different coordinate systems, and trying to make control work across modes in a more elegant way. But I do think as a mathematical framework for stiff impacts, it's a very, very good way to go. Cool. I will end there, and sorry I spent too much time on cockroaches.